we've been hinting about equilibriums, but we haven't actually discussed equilibriums, and now we're going to do it. We're going to discuss what an equilibrium is and how those equilibriums can be altered or changed and what factors affect them. So initially, let's look at what an equilibrium is. So mercury oxide, this is an example from your book. If we heat it up, it'll decompose into liquid mercury and oxygen gas. However, if we heat liquid mercury and oxygen gas up gently, they'll form a mercury oxide. So we have a reaction that can go either way depending upon the conditions, and actually both of those reactions will occur simultaneously. So what this means is, this is when we draw this double arrow to show that this is really an equilibrium. What an equilibrium means is not only can the reaction go either way, so it will go the other way and at the same time. So when we've reached what's called thermal equilibrium, the reaction has not stopped. That's an important thing to remember. Notice there's a reaction rate here. The reaction rate hasn't gone to zero. It hasn't stopped. The reaction is still progressing. However, we've reached a point where this forward reaction rate has balanced with the reverse reaction rate. So the rates are equal. So the reaction is still happening, but the forward and the reverse rate are equal. So the other thing that we can see is when we've reached that equilibrium, okay, so we have that point of equal rates, just like in that first graph there. Now at that point, the amounts is really not the best word. The concentration of, say, our products in this case, and the concentration of our reactants here, they're not equal. Notice they're not equal on this graph, but they're not changing. So there's no change in the concentration at the point of equilibrium. So we've reached a point where the forward and the reverse reactions are equal, so the rates are equal, and our concentrations are remaining constant. So again, it doesn't mean that the reaction is not happening. So this reaction is happening. These are still going together to make mercury oxide. Mercury oxide is still breaking apart to make mercury and oxygen. But those rates are equal, so it looks like we have the same amount, really, of stuff on either side. The stuff amounts aren't changing. Now again, just like this graph shows, it doesn't mean that we have the same amount of stuff. It's not the same amount of stuff. An equilibrium could make mostly products, or it could leave mostly reactants, but the concentrations on either side are not changing. So very important, very important. The reaction is still happening, but the rates are equal. So we have the same, the numbers of stuff on either side are not changing anymore. Okay. So how do we define that how do we quantitatively define that equilibrium? Well, we do it based, really, it's just on a ratio of the concentration of products over the concentration of reactants. We just compare. So notice this isn't too terribly difficult. The more products we have, the larger our K is going to be. So if the product concentration goes up, if we have more stuff on this side, then we have a bigger equilibrium constant, and that means the reaction lies further, again, to the product side. Again, it doesn't mean it's not an equilibrium, it's just we're going to have more products than reactants as far as a ratio. Now, notice if we have a small amount of products and we have a large amount of reactants, if this number is really big, well, that's going to make our K value really, really small. So if we have a really small K value, that's telling us that most of our stuff is actually on the reactant side. It is an equilibrium, but the amount of products and the concentration of products is very, very small. Now notice how we write this equilibrium constant. We write it the concentration of the stuff there to the power of whatever coefficient is in front of it. Kind of interesting. So let's look at an example. Oh, okay, we can define it. So an equilibrium constant, like I said, is really just a mathematical ratio of the concentrations of our products at equilibrium to the concentrations of our reactants. So again, we're just looking at how much products did we make, how much reactants are left. The more products, the bigger our equilibrium constant, means things lie to one side. So here's another example, or a real example of writing an equilibrium constant. So hydrogen and iodine, and here's the example of it. So hydrogen and iodine are mixed in this cylinder here. They start reacting. Notice that purple color goes away slowly, but it doesn't ever completely go away, because this reaction goes in both directions. So there, again, it's reached chemical equilibrium. So there's initial reaction, but at some point it reaches chemical equilibrium, where the forward reaction is equal to the rate of the reverse reaction. Now, that doesn't mean the stuff on both sides are equal, but the rates are equal. So what we want to determine at that point then is what is that equilibrium constant? Well, K that we'll use for equilibrium constants is the ratio of the products raised to their power over the reactants. Product of the reactants raised to their power. And in this case, notice our product is hydrogen iodide, HI, raised to the second power over hydrogen gas times the concentration of iodine gas. So if we know the concentration of the gases, then we can determine what the equilibrium constant is. Very good? Very good. Okay, so now notice here's a bunch of values for that particular reaction. So they have the concentration of hydrogen gas, the concentration of iodine gas, the concentration of hydrogen iodide. Plug those into the formula, we get our equilibrium constant. Now what this equilibrium constant is telling me, because it's bigger than 1, it is telling me that this equilibrium lies towards the product side, towards the hydrogen iodide. And if we look at these values, notice this is 0.49, 0.49, and this is 3.6. Now they're all to the same exponent, so there is a larger concentration of products than reactants. If these values are bigger than 1 or much bigger than 1, we can assume that our equilibrium lies towards products. Now notice they plugged in different numbers, different concentrations, and notice the equilibrium constant is, well, close to being a constant. Notice they don't get the same value each time. It is an experimentally derived problem, so there is some inherent error or random error in these values, but again, relatively they're a constant. So it doesn't matter what concentrations we put in, they should all eventually reach the same equilibrium constant. Now be careful, because this equilibrium constant can be influenced by things like, well, temperature might influence our equilibrium constant, but we'd have to look at that here in a separate podcast. I'm going to do another one here. We have an equilibrium mixture of N2, O2, and NO gases. So we have N2 mixing with O2 in an equilibrium reaction making NO2. So now we're given a bunch of concentrations. We are given the concentration of nitrogen, the concentration of oxygen, and the concentration of nitrogen monoxide. We're asked what's the equilibrium constant for the system at this temperature. Notice it does say at this temperature because equilibrium constants are temperature specific. Just like in the previous reaction rate constants are temperature specific. So we have K. It is going to equal, if we write the equilibrium constant, NO squared, because that's our product, over N, concentration of N, and the concentration of O. One thing to be aware of is these are concentrations, right? So in this case, we have nitrogen gas, oxygen gas, and nitrogen monoxide. Now they're all gases, so they all go into the equilibrium constant. But let's look at a scenario like, I don't know, say hydrogen gas is reacting with oxygen gas in an equilibrium, and these are both gaseous, and they're in an equilibrium, and say they're making liquid water. Well, liquid water doesn't have a concentration because it is a liquid. Liquids and solids they don't have concentrations, they don't go into equilibrium constants. So if I wrote an equilibrium constant for this reaction, it's going to look a little silly, but it would be 1 over the concentration of hydrogen times the concentration of oxygen. Because that's a liquid, we wouldn't include it in the equilibrium constant. Now, if it was a gaseous, then we would. Let's do a different example. Say we had sodium chloride as a solid. We put in water and we get sodium ions and chlorine ions. And maybe we assume it's in equilibrium. We want to write what's the equilibrium constant. Again, this is a solid, so it doesn't have a concentration. So our equilibrium constant is simply the concentration of sodium ions times the concentration of chlorine ions. It's not divided by anything because this is a solid, so it doesn't become part of our equilibrium constant. So just one thing to be aware of when we're writing these is that, again, we are only concerned with things that are in concentration. Aqueous items, gaseous items, liquids and solids, we just drop out of our equilibrium constant, our equilibrium calculation. Okay, so again we have the expression written based upon the balanced equation. Now for this one it's pretty easy. We can just plug the numbers in. I have 1.1 times 10 to the negative fifth. That value has to be squared because that's our nitrogen monoxide value, all divided by the 6.4 times 10 to the negative third, and that multiplied by 1.7 times 10 to the negative third. Now what you might want to do when you're doing this calculation is you may want to take care of your exponents first, and that's what I'm going to do here. So I have 10 to the negative fifth squared, so 10 to the negative fifth times 10 to the negative fifth. We'd add those exponents, so you have negative 10th, 10 to the negative 10th, and then I'm dividing by a negative third times a negative third, so I'm going to subtract essentially a negative 9, so we'll be adding 9, so this is actually 10 to the negative first. So I do my exponents separately because I don't want to put them into the calculator, but then I can just divide my numbers. 1.1 divided by 6.4 and divide it by 1.7. And I can answer that's 0.1 times 10 to the negative first, or we could just say 1 times 10 to the negative second, I guess, if we wanted to change that. And that's the equilibrium constant, again, at that temperature. It is temperature specific. Let's look at a couple of the questions at the end of the section. It says hydrochloric acid is a strong acid, dissociates completely in water to form hydronium ions and chloride ions. Would you expect the value of K for the reaction to be 1 times 10 to the negative second, 1 times 10 to the negative fifth, or very large? Justify your answer. Well, if it completely dissociates, that means we're going to have large concentrations of this, and a very small concentration of hydrochloric acid, if any at all. So our K constant should be very large, because the K for this would be the hydronium ion concentration times the chloride ion concentration all over the hydrochloric acid concentration. So because it completely dissociates, these two values on the top would be very big. This would be very small, leading to a very large K. Now notice I didn't put water into the equilibrium expression because it is liquid water and does not have a concentration to speak of. So let's write an equilibrium expression here. We have a nice reaction. Notice this is a homogeneous reaction, meaning it's all in the same state. They're all gases. Since they're all gases, we'll include all of these values. We'll have gaseous water squared times chlorine squared. So it's the product of the products raised to their power over the reactants raised to their power. And again, we include anything that could be in a concentration. We include gases, we include aqueous things, we don't include solids, so no solids and no liquids in our equilibrium expressions. So all the other ones are writing expressions, plugging in numbers. Number 9 here is a little bit different. It says we have this reaction, we'll write the equilibrium expression for it first, which is what we always have to do in these scenarios. So it says we have this, and there we go. It says at 425 degrees Celsius, calculate the hydrogen iodide concentration. So this is what we want. Given that these two concentrations are equal, they equal 4.79 times 10 to the negative fourth, and the K value is 54.3. Okay, so we just have to rearrange the equation. Well, if I'm rearranging the equation, I'm going to first multiply both sides by the hydrogen ion concentration and the iodine concentration. That'll cancel these out here, but then I have to move it to the other side, so I'll have hydrogen iodine concentration squared equals K times the hydrogen ion concentration times the iodine concentration. Now we want to get rid of that square, right? Well, the opposite action of squaring something is we'll just take a square root. We'll take a square root of this side, so the hydrogen ion concentration is going to equal the square root of 54.3, which is our K value, times 4.79 times 10 to the negative fourth. And because these two are the same, I can just square that value. And if I run those values through, I get a hydrogen ion concentration. You can check this. I'm maybe wrong here. 0.00, I get 353, or 3.53 times 10 to the negative third is my concentration of hydrogen iodide. So notice we have much more of it than we have of either of our reactants. So this equilibrium, like it says, is lying to the product side.